On the periodic table, which is very useful to chemists, there are some patterns, some periodic properties, there's some columns called, that will allow you to quickly tell which atom is bigger or smaller, or more into electrons, or more metallic, lots of different things. Now, these are just trends. They're a little cheesy, but they do sometimes help when asked random questions at different times. And the four we're going to look at in this particular section, more than anything, are the sizes of atoms, both the atoms and the ions, the ionization energy, how much energy it takes to remove an electron, the electron affinity, which is actually an energy change when electrons are added, and we'll also briefly talk about what's called electronegativity, which is how interested elements are in attracting electrons. Now, electronegativity is going to be more for the next chapter, so I won't talk as much about that here, but we'll talk about the first four and how the periodic table can be used to figure these things out. Now, punchline here is that sizes of atoms and ions will get bigger as you go left and down the periodic table, and all the other ones will get bigger, more or less, as you go up and to the right on the periodic table, and we'll talk about this here in a little bit. Sizes generally get bigger as you go left and down the periodic table. And this can be kind of helpful. So these are actual radius values of the atoms in group 1A, hydrogen, lithium, sodium, potassium. And those numbers there are in picometers. A picometer is 10 to the minus 12 meters, so pretty small. But what I want you to see here is that all those atoms are getting bigger as you go down. So as you go down the periodic table, from hydrogen to lithium, lithium to sodium, the atoms do get bigger. You have more protons, more electrons running around, pretty crazy. So atoms get bigger as you go down the periodic table. They generally get bigger as you go left across the periodic table as well. The atoms on the right kind of tend to get shielded a little bit, and the atoms on the left don't. So this is an example of chlorine through sodium, and you can see that pretty much the atoms are getting bigger as you go left. So someone asks you a question, i.e. your instructor, which atom is bigger, sodium or magnesium? You would say sodium, because sodium is more left on the periodic table than magnesium is. And if I asked you which atom was bigger, rubidium Rb or sodium Na, you would say rubidium Rb, because that's more down on the periodic table. And if you know that, that's pretty awesome. That's all we need to worry about. This picture shows a lot of atoms from the periodic table, and I just want to highlight how this is not perfect. Now, earlier we said that sizes get bigger as you go left and down, and there are definitely some examples where the atoms are not getting bigger. So antimony is not bigger than tellurium, all right? Even though antimony is more left, it is smaller, all right? And that's just something to think about. On the other hand, arsenic there is bigger than germanium. So germanium is more left, but arsenic is bigger. So again, these rules are a little bit cheesy. However, if you're in the hallway and you don't have access to Google and stuff, and someone from Chem 104 or whatever asks you, which atom is bigger, Dr. Russell, rubidium or strontium? Well, now you know my secret. More often than not, left is bigger as you go on left on the periodic table. So rubidium bigger than strontium. And the same thing for down. So barium would be bigger than strontium, stuff like that. But again, it's not perfect. This is a question you might see. It says, which of these has the largest atomic radius, the largest size? And again, you want the atom which is most left and down on the periodic table. So if you have a periodic table next to you, definitely the one that's most left and down is sodium. Sodium is most left and down on the periodic table. Carbon is be most up and to the right. You'd go left to boron. You'd go down a little bit and left to aluminum. I guess just left to aluminum. And then sodium is the most left and down of all. So that would be how these work. Again, they're not perfect, but it works more often than it doesn't, and that's why it's worth talking about. Now, when it comes to ions, we have to distinguish here between cations, positive ions, and anions, negative ions. So if lithium goes to lithium plus, it loses an electron. And lithium plus has 2 electrons and 3 protons. So the protons are able to hold on to those 2 electrons a lot better than if you have 3 protons and 3 electrons. So notice that 152 picometers for neutral lithium goes to 60 picometers for lithium plus 1. cations are always smaller than the atoms from which they came from. You have more protons able to hold on to those electrons. Those electrons kind of shrink in a little bit. So cations are always smaller than the neutral atoms they come from. However, if you're making an anion, so for example, we're going to talk about fluorine here going to F-1 fluoride, then we're going to see that those generally are bigger than the atoms they came from. So anions are bigger than the atoms they came from, while cations are smaller than the atoms they came from. And that'll be important here for a little bit. However, if you look at all the sizes of the ions on the periodic table, and if you're able to understand that anions, which are kind of to the right of my line, versus cations on the left, then generally you can see that generally atoms get bigger, ions get bigger, left and down. But you should really only compare one to the other. You shouldn't compare like cations and anions together. All right? So the anions are the black ones on the right-hand side, and the cations are the black ones on the left-hand side. So let's focus just on the cations. Beryllium is smaller than lithium, so that means lithium is bigger. Going left makes it bigger. And also, if you go down, you can see that sodium is bigger than lithium, rubidium is bigger than potassium, etc., etc. So in terms of just cations, left and down works really well. Now on the right-hand side, we need to look at the black lines as well. And generally speaking, left and down works well. But you can only compare anions to anions and cations to cations. You can't compare anions and cations together or stuff like that. Now, like before, there are exceptions. So telluride, T2-, is smaller than iodide, which is 220 picometers. So again, they're not perfect, but overall, it's a fairly good thing. Although now that I say that, I just realized selenium is smaller than bromide. Well, anyway, ultimate answer, if you can look these things up in Google, something like that, of course it's better. All right, because then you have the actual numbers to look at. But again, someone from Chem 104 talks to you outside the bathroom or something and says, which one's bigger? Even you now can say, well, left and down works pretty well, but only compare cations to cations and anions to anions. So here's an example of a problem you might see. It says, which of the following should have the largest radius? These are all anions with a neutral atom. But what's important here is they're all on the same level of the periodic table. So left and down is what you generally want to follow. So argon would be most on the right, chloride would be next, sulfide would be next, and phosphide, P-3, is most left and down. So for all of those, we would say for that reason alone that phosphide is the biggest. Now, you can also think about it in terms of protons and electrons, and you can see here how phosphide has fewer protons. They all have the same number of electrons. So the more electrons there are per proton, the bigger the atom's going to get for that reason too. So phosphide will certainly be the biggest of all of those ions. Ionization energy is the energy required to move an electron from an atom. And there's different types of ionization energy. So the first ionization energy would be the energy required to remove a single electron. A second ionization energy is possible, though, too, because you can take that now singly ionized atom and remove a second electron from it. So the first ionization energy is the energy required one electron, and the second ionization energy would be the energy required to remove the second electron. Now, metals lose electrons a lot more easily than the nonmetals. So generally speaking, ionization energy is the opposite of our sizes. Ionization energy generally increases up and to the right on the periodic table, so the opposite of the sizes. Now, like everything, ionization trends are just kind of a trend, and they're not perfect. But you can see there helium versus hydrogen. Helium is more up and to the right, so it definitely has a higher ionization energy. And when you look at lithium through neon, generally, it goes up and to the right. The energies increase. But look, nitrogen is higher than oxygen, and beryllium is higher than boron. So there are some deviations amongst this. It's not totally perfect. But again, again, someone accosts you in the middle of the hallway and you don't have access to Google or don't want to look it up, whatever, generally speaking, up and to the right works better. So you can see here, helium is most up and to the right. It's higher than neon, which is the top of the next one, which is higher than argon, etc., etc. Electron affinity is the energy change that happens when an atom accepts an electron. And there's lots of differences here. Electron affinity, in my opinion, is the weakest of these trends. But for some elements, energy is actually released, like you get energy out. It's exothermic. Other ones, it's positive. It can be all over the place. Electron affinity is not always as helpful as ionization energy, and the sizes are they, but that's a cool thing to think about as well. Some elements require energy to have the electron added in. Some of them have energy given out. It just kind of depends on the different element you're looking at. But again, more or less up and to the right is the way to think about this. But again, it's not perfect. Now, up and to the right is by far the cheesiest. So first of all, helium doesn't want to add any electrons, so it doesn't count in this game. And generally speaking, though, it's up and to the right. But one thing that's always perplexed me is why, if you look here in the upper right hand corner, why in the world chloride is higher than fluorine? Like, why making chloride you get more energy out, negative, than if you made fluoride? So it's kind of, I hate to say cheesy, but electron affinity is less helpful, shall we say, than others. But if you're asked a question, up and to the right is the name of the game.